Okay, good. So the next speaker is Josep Lumbreras from Singapore, and he will talk about quantum bandits. Please go ahead.
Okay, thanks organizer and the committee for the opportunity. I'm going to present the problem of multi-armed quantum bandits. It has been a joint work with Dr. Erkka Haapasalo and Professor Marco Tomamichel. And well, if you are interested, here you have the archive reference. Okay, let's start. First of all, I will review the multi-armed bandit problem. It's a classical problem. So I will start with an example. Suppose that we are in a casino and we have some of these slot machines, and we want to detect the slot machine that gives us the highest reward, because each of these slot machines follow a slightly different probability distribution. So the thing that we want to do is we want to explore all these slot machines, so pulling the arm and observing the rewards. But at the same time, we want to exploit the slot machines that apparently gives us the highest reward. So this is a trade-off in this learning problem of exploration versus exploitation. So we want to explore all these slot machines, but at the same time we want to exploit those ones that give us the highest reward. So more formally, we can formulate the multi-armed stochastic bandit problem as follows: is that we are given a set of an unknown probability distributions to a learner, xi from 1 to k, and we have a learner that over n rounds interacts with this probability distribution. So it selects one of these probability distributions and samples a reward. And what the objective of the learner is to maximize the total cumulative reward. So this is one of the simple model of decision making with uncertainty. And as I said before, it's a trade-off between exploration and exploitation. And there are a lot of practical examples. So one can be, for example, slot machines, or you can, for example, model as a bandit problem, problem of restaurant selection. So, for example, you want this night I want to go to dinner to some restaurants. So I know some restaurants that are good, so I can explore those ones, or I can explore to some unknown restaurants with the risk that maybe they are better or maybe they are worse. So yeah, this is just a few examples. We have extended this stochastic bandit problem to a quantum learning scenario, and this is the multi-armed quantum bandits. And the model is described by two things. One is a set of quantum states that we call the environment, and the other one is the set of observables that we call the actions. So the observables are just Hermitian operators, and we define two types of bandits. One that are with discrete and finite action set. So this action set is just a finite set of observables, or a bandit with continuous action set that are action set that contains, or for example, a particular example is, for example, a set of all rank 1 projectors. So the bandit problem is characterized by the tuple of actions and environment. So thing to remember here is that actions are observables and environment are a set of quantum states. So how the learner interacts with the bandit, it goes as follows. The learner will interact over n rounds with the environment, so with a known quantum state from this set of quantum states. What we'll do is, at each round, the learner will select one observable from the action set and will perform a measurement on the non-quantum state. And from this, we'll sample a reward with the probability distribution associated to the quantum state and the observable. So this strategy of the learner is determined by what we call a policy. And a policy is just an algorithm that tells you at each round what observable to select. So you will be selecting observables and sampling rewards, and from this information, the learner is the information that the learner will use to decide which observable to pick next. So this is how the learner interacts with the bandit. Now, what is the objective? Well, this is a scheme of how it works. So yeah, the learner uses the past observations in order to decide the next observable to pick from the action set. So what is the objective of the learner? So the learner wants to find the action, so the observable in the action set, that in expectation maximizes the reward. So this means that it wants to find the observable that has maximum overlap with the unknown quantum state. So this is equivalent to minimizing the expected cumulative regret. That is the following expression that we have here. That is just a sum over n rounds of the relative loss that the relative loss is defined as follows: is just the difference between the maximum expectation value that we can have. So it's a maximization of the trace of the non-quantum state and maximization over all the observables in the action set, minus the expectation of the trace of the non-quantum state and the observable that is selecting the learner at round t. So here there is we have to take into account that this observable is a random variable since it's the choice of the learner. So this is determined by the strategy. So that's why here there is the expectation value here. And special cases of the regret is, for example, if the action set contains all rank 1 projectors, minimizing the regret implies finding the maximum eigenvector of the non-quantum state. More specifically, one of the cases that we study is that if the non-quantum state is also pure and the action set contains all rank projectors, then the regret can be expressed as follows. That is the sum of from 1 to n of the expectation value of this is the trace distance between the non-quantum state and the rank 1 projector, trace distance squared. So minimizing the regret implies minimizing this trace distance. In this can be seen as online quantum state tomography with minimal regret. So the regret that I explained before is just for a particular state, but we're interested in the following regrets. That is, one is the worst case regret that has the following formula that is given a set of density matrices, that is the environment, is just the worst case regret, which means that it's the supremum of the over all possible regrets, or the supremum is taken for the unknown quantum states in the given set. So this worst case regret, it tells us how well a policy, so a strategy for the learner, performs for the given set of unknown quantum states, so the environments. So, and then the minimax regrets is defined as the best thing that that can achieve a policy over all these worst case regrets. So it's a minimization of the worst case regret over all set of policies or over all set of strategies. And the minimax regret is it tells how difficult is the problem given by a set of environments in a worst case scenario. So
a quick question here, maybe.
Yeah.
So how can we see, just to get used to the notation, how can we see the classical case you mentioned at the beginning as a special case of this? Can you say what rho is and what
yeah, sure. So here, in the classical case, what you have is probability distributions, no? So the regret is just the difference between the best, say the highest mean of this set of probability distributions and the mean of the probability distribution that you are playing at this time step. So the analogous will be that, for example, the rows is just, for example, a possible set of probability distributions that, for example, can be Gaussian distributions or whatever, and the actions is just a set of indices that tells you which action to pick.
Okay, great, thanks.
Yeah, so what we have to keep in mind is that the formal regret is just the relative loss between the expectation value of the best thing that you can do, so the best observer that you can choose, and the one that you are choosing at each round. So, and this minimax regret is, as I said before, it tells just us how well performs a policy for a given problem. That, remember, the problem is given by the set of actions and the set of environments that actions are observables, and the environment are the set of quantum states. So the goal of this work is to give bounds on these minimax regrets for different set of environments or quantum states and set of actions, so observables, in terms of the number of rounds n, so the number of rounds that the learner interacts, and the dimension of the Hilbert space where the quantum state and the observable lives. So we differentiate between lower and upper bounds. So for the lower bounds, we will use an information theoretic techniques to derive the lower bounds. And for the upper bound, we'll find algorithms and we'll analyze the regret. Yeah, so I started describing the general case where the environment So the set of unknown quantum states, we let that this be to any quantum state. So it's just a set of mixed states for a given dimension D. And the action set, we consider a finite set of observables. So from observable 1 to observable k. Note that if we don't impose any condition on the action set, we have a trivial lower bound. Why? Because there is, for example, a simple example that if the action set is only, there are only two observables, and one is bigger than the other in a matrix sense, then we have that for any quantum state rho, the expectation of one of these observables will be always greater than the other. And this implies that since the minimax regret is a minimization over all policies, there is always a policies that choose as action the observable one. So the regret will be always zero because we are always choosing the best action. So in that case, we define what we call a dominating condition. That is that we say that an observable is dominating in action set if the overlap of this observable with its maximal eigenvector, so the eigenvector of this observable with highest eigenvalue, is always greater than the overlap of this maximal eigenvector with any other with any other observable of the set. So the first result that we have is that if we consider discrete multi-armed quantum bandit, where we let the action set is discrete and the environment is any quantum state, then for d greater or equal to 2, if the action set is comprised of traceless observables and contains at least two dominating observables, we have the minimax regret scales with a lower bound of square root of n. So now I will give a very brief sketch of how we prove these lower bounds just for this case. Every case has some specific calculation, but you can go to the paper to see this. So I will give just an idea. So for the proof of the lower bounds, we use the following inequality, that is the Bretagne-Haber inequality, that tells us the following: that if we have two probability measures, P and Q, on the same irreducible space, and we have an event on this space, that's an arbitrary event, then we have that the P of A plus Q of the complementary of this event will be always greater than 1/2 of the exponential of minus the divergence of these two probability measures, where the divergence is just the standard Kullback left-right divergence, so classical divergence. So how the proof works? So we need to find environments, so quantum states that we know that for every policy will perform bad. And we propose two of these quantum states. So in order to do that, what we do is we pick, we have in the conditions of the theorem that there are at least two dominating operators. So we choose, from these two operators, we choose their maximal eigenvectors, and we will propose the following quantum states that are just a mixture of the identity operator plus some perturbation of these maximal eigenvectors, and this parameter will be fixed later. For the moment, it's between 0 and 1. And then the regret that I showed you at the start can be reformulated as follows. Now, instead of being a sum over all rounds, it's a sum over all possible indices on the action set. So if we have k observables, it's a sum from 1 to k of the expectation of the number of times that we have played each observable up to RAM n. So this first term is just, it tells us the expectation of the number of times that we have played observable I up to RAM n. And then this is the relative loss between the best action and the observable. Actually, this T should be an I. So it's the relative loss between the observable I and the best observable. So with these things, choosing carefully two sets of indices of the set of observables, we can bound the sum of the two regrets for the two quantum states that I showed you before as proportional to n, the parameter delta, and the probability. Well, now we don't have to go into this, but the probability of two complementary events. So since we have that, we can apply the Bertrand-Haber inequality plus data processing inequality to go from a classical divergence to quantum divergence. And in general, we have that the sum of the two regrets is bounded by some constant that depends on the action set, and delta, and the exponential of minus n, the quantum divergence of the two quantum states. And then the proof is completed just seeing that this divergence is greater, is less or equal than something that goes as delta square, and then choosing delta as 1 over square root of n, the proof is complete. So this is the only proof that I will discuss in this talk. So the other examples that we study work in a similar way, how they are proven. So for example, then we study some specific cases. So this case is a case where, again, is a discrete multi-armed quantum bandit. But in this case, the action set is just a Pauli observable. So we allow that the action set, the set of observables has k different Pauli observables. And then we can bound the minimax regret as follows. So as before, it goes as square root of n. But now we can introduce the factor that goes as k minus 1, so where k is the number of Pauli observables. So k minus 1 is natural because if we have only k equals to 1, so only one observable, there is only one action, so you are always to pick the right one. So this is why this minus 1 comes from. And then instead of considering, we study also action set that instead of being discrete action set, we allow continuous action sets. So in particular, we allow that the action set consists of all rank 1 projectors in the dimensions. And here we can show that the minimax regret scales as square root of n with a lower bound. So now I'm going to discuss the upper bounds. So for this, we use an algorithm. So now we will discuss the algorithm that can achieve the scaling of the regret. So in order to do that, we work on our vector representation of the quantum state and observables. So using orthonormal basis for Hermitian matrices, we can decompose the quantum states on the observable as follows, that it can be solved just as the inner product of a real vector and the set of Hermitian matrices that are the sigma I, that from 1 to d square, where d is the dimension of the Hilbert space. So now the mean of each action, for the quantum states, we associate the vector zeta, and for the action OI, so the observer OI, this vector AI. So then the trace of rho OI can be seen as just as the inner product of zeta and AI, so the vectors associated to rho and the observable. And how the algorithm works. So at each round T, after observing the rewards, so that are sampled from the interaction of the observable with a non-quantum state, and after observing the rewards and the observable that we have played, we can approximate the vector that encodes the known quantum state with the least square estimator. So this formula is just the formula of least square estimator for the vector zeta at round T. So, but what the algorithm does is it uses this estimator for the vector of the non-quantum state, and it builds a confidence region that it actually is like an ellipsoid, and would tell us that in this ellipsoid with high probability we will find the real vector that encodes the quantum state. So, and it's centered in this least square estimator. So what does the algorithm does a very simple thing. So at each round, it constructs a confidence region for the unknown vector, and then from in this confidence region, it finds like it finds the vector zeta that maximizes the inner product over all possible actions, and then the algorithm selects the best action of this maximization, and will play the observable associated to this action and observes the reward. So this is just an adaptation of the classical algorithm LinUCB for classical multi-armed stochastic bandits. So it's just an application of the classical algorithm. And the scaling that achieves is a scaling that goes as square root of n, and d squared, the dimension, and logarithm of n. So one question that we have here is can we find a quantum version of this LinUCB algorithm, for example? Because this is just an adaptation of the classical problem. So actually, this is a table of our lower and upper bounds. So for discrete case, we can match lower and upper bounds. So they scale always as square root of n. And we differentiate between arm limited and dimension limited. Unlimited means that the number of observables is less than the dimensional square. And dimension limited, it means that we allow a rated number of observables. So the scaling goes, for example, for arm limited as square root of kn, and for dimension limited, d square root of n. So in this case, we can match lower and upper bounds almost optimally. There is some logarithm terms, but where we don't have perfect matching is in the continuous settings, where the observables are all rank bound projectors. Since our lower bound goes as the square root of n, and the upper bound goes as d square root of n. Actually, the algorithm that I explained is LinUCB, but there are some variants of LinUCB that we apply to the discrete case in order to match the lower bounds, but they are similar algorithms. Just to apply to these specific cases. So yeah, now I will briefly review the other environments that we studied, because now we have studied environments or non-quantum states that can be any possible quantum state, but then we focus on pure state environments. So now the environment is just the set of pure states. Yeah, one result that we have that, for example, for the simple case where the environment are just pure states in two-dimensional Hilbert space or in qubits, and the action set is just the polymetrices. Well, we don't have anything surprising that the minimax regret, the lower bound scales as square root of n. But what happens is that if we study the same problem with environment of pure states, but the action set contains now all rank 1 projectors, then I explained before the regret can be expressed as the sum of the square of the trace distance between the non-quantum state and the state that you select at each time step. But here we are unable to prove a non-trivial lower bound in this case. So for this case of pure state environments and all rank 1 projectors as the action set, we consider the trace distance regret. So it's the sum from 1 to n of the expectation value of the trace distance between the non-quantum state and the action. So here there is not a square. In this particular case, the lower one that we achieve is it goes as square root of n. But here we have to be careful, because now this is no longer the same regret as before. So is this regret that we introduced that square roots in every term. So it's this trace distance regret. And yeah, now for finishing, just if we try to apply the same algorithm that I explained before, LinUCB, for this specific case of pure states, the analysis shows that in the trace distance regret, the scaling goes as n3 over 4. So it doesn't match this previous lower bound of square root of n that I show. So, but actually, if a simple variant of tomography achieves a better regret of n that goes as n to the 3. And yeah, this is a sample. Yeah, this is very simple variance tomography, because the only thing that we do is that we base this algorithm in the project least square estimator, that is this paper that fast state tomography with optimal bounds. And this algorithm is very simple. It has only 2 parts. During the first n to the 3 rounds, it just performs polyobservable measurements of the non-quantum state. So here we don't care about exploring or exploiting. We only perform measurements. And after collecting this data, we build an estimator for the non-quantum state, and we ensure that this estimator is pure. So when we have ensured this, for the remaining rounds, we just play this estimator as our action, because now our action set contains all rank 1 projectors. So this estimator is also in our action set. So here's a summary of the algorithm. Just 2 parts: the part of collecting the data from polyobservable measurements, and then here you just build the estimator and you just play the same estimator at each round. Yeah, just for summary of results. So we have the lower and upper bounds. We have that they match for the discrete case. So discrete case of actions. But we have a gap of d squared for general bandits, so that they contain all rank for continuous action set with rank 1 projectors. So we have this gap of d squared that I commented before. And then I think that the best open problem that we have is that in this pure state case, as I showed you before, when the actions are all rank 1 projectors and the environments are pure states, we have that the lower one bound scales for the trace distance regret at square root of n, and actually the normal regret it's just a triple lower bound. And we think that here we can find like better strategies for pure states that can beat the, for example, for the normal regret, it can beat the typical square root of n that we have in every example that we have studied. And actually, for this trace distant regret, the upper bound goes as n to the 3, but actually it's a very naive upper bound because this algorithm is not very adaptive. So thing to keep in mind is we conjecture that the regular regret for this case scales slower than square root of n, and actually we think that can scales just as a logarithm of n because our triple lower bound is constant, but we think that it cannot be improved, but we need to find this strategy. So yeah, I think that this was all.
Okay, thanks a lot for this talk. Are there any questions?
So I have a question, comment. Okay.
I cannot hear you very well.
I have a question. I have a question. Can I make it so? So first one is you discuss the regret, but I cannot find the meaning of regret. Could you explain the intention of the definition of regret?
Sorry, can you type the question in the chat because I cannot hear the audio. Oh, the meaning of the regret. Yeah. So because the thing that you want to do is to can you see my screen? Okay. Yeah, can you see my screen now?
Yes, sir.
Yeah. So the objective of the learner is to find the observable that has maximum overlap with this quantum state. So as you see here, the regret is just the relative loss between the best thing that you can do, so the best observable that you can pick, and the observable that you're picking at round t. So what you want to do is to minimize this quantity, because if you match at round t, you are choosing the observable that maximizes this trace of rho OI, then the regret will be 0. So this is like the relative loss that you have at each round. So, and what you want to do is to minimize this, because as soon as you have like regret 0, the regret is constant at some point, it means that you have learned the best observable. So this is the meaning of this regret. So it quantifies the relative loss of this learning task.
I cannot understand. So what is A? A is a what kind of set?
What?
A. What is A? Calligraph A. I cannot understand. Yes. What is this?
This is the action set, so the action of observables. So it's just just an argument of the set of possible observables that you are quantifying this regret.
What is pi?
Pi is the strategy. So it's what is the probability distribution associated to the learner. So it's like the strategy that is following the learner to select the observable at each round.
Why this one can be considered regret?
Sorry, what?
Why this is regret?
Rigorous, you mean?
Why? Reason. Why this one is called regret?
Why is it called regret, I think?
Regret. Oh, okay. I mean, we have just taken the name from the classical bandit problems that quantifies the learning task. I mean, specific name, I'm not sure why it's, I mean, regret, because I don't know, in all these online learning tasks, you have these regrets that quantifies the relative losses between you are learning.
Okay, so in the interest of staying in schedule, I suggest we continue this discussion over Slack. Is there just a quick question by any other participant? If not, let's thank Josep again. And